हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज मैं करने जा रही हूँ क्लास 11 की यूनिट 9 हाइड्रोजन। बहुत दिन से बच्चे इसकी डिमांड कर रहे हैं, तो आज इसका एक ही वीडियो में मैं आपका कंप्लीट कर दूंगी हाइड्रोजन चैप्टर। सो आई होप कि आपकी तैयारी भी अच्छी चल रही होगी, बट उनके बारे में सोचिए जिन बच्चों को अभी नहीं पता है कि ऑडियो बुक्स भी अवेलेबल हैं इस तरह से यूट्यूब पर। तो आपकी ये फर्ज बनता है बच्चों कि आप लोग अपने दोस्तों के साथ में ज़्यादा से ज़्यादा इसको शेयर करिए, ताकि उनको भी उनकी प्रिपरेशन में हेल्प मिल सके और वो आपको फिर ब्लेसिंग्स ही देंगे, राइट। सो चलिए स्टार्ट करते हैं, टाइम वेस्ट नहीं करते हैं। अगर आपको ये वीडियो लगे, आपकी हेल्प कर रहा है, तो इसे लाइक कीजिएगा और अगर चैनल पे नए हो तो सब्सक्राइब कर लीजिएगा, क्योंकि यहाँ पर आपको ऑलमोस्ट वो सारी चीजें मिलेंगी जो आपकी तैयारी को बूस्ट अप करती हैं, वो भी कम से कम टाइम में। तो चलिए स्टार्ट करते हैं। यूनिट 9 हाइड्रोजन। Hydrogen, the most abundant element in the universe and the third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as a diatomic molecule and is called dihydrogen. It forms more compounds than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is a great industrial importance, as you will learn in this unit. 9.1 Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that the elements in the periodic table are arranged according to their electronic configurations. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration ns1 of alkali metals, which belong to the first group of periodic table. On the other hand, like halogens with ns2 and p5 configuration belonging to the 17th group of the periodic table, it is short by one electron to the corresponding noble gas configuration, helium 1s2. Hydrogen therefore has resemblance to alkali metals, which lose one electron to form unipositive ions, as well as with halogens, which gain one electron to form uni-negative ion. Like alkali metals, hydrogen forms oxides, halides and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Delta IH of Li is 520 kJ per mole, fluorine is 1680 kJ per mole, and that of hydrogen is 1312 kJ per mole. Like halogens, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogens, it differs from them as well. Now the pertinent questions arises as where should it be placed in the periodic table. Loss of the electron from hydrogen atom results in nucleus of approximately 1.5 into 10 to the power minus 3 picometer size. This is extremely small as compared to the normal atomic and ionic sizes of 50 to 200 pm. As a consequence, hydrogen does not, or H ion does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is therefore best placed separately in the periodic table. Unit 3. 9.2 Dihydrogen H2. 9.2.1 Occurrence. Dihydrogen is the most abundant element in the universe, 70% of the total mass of the universe, and is the principal element in the solar atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it is much less abundant, 0.15% by mass, in the Earth's atmosphere. Of course, in the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrides, including hydrocarbons, and many other compounds. 9.2.2 Isotopes of hydrogen. Hydrogen has three isotopes: protium, deuterium, and tritium. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinary hydrogen protium has no neutrons. Deuterium, also known as heavy hydrogen, has one, and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotopes of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156% of deuterium, mostly in the form of Hd. The tritium concentration is about 1 atom per 10 to the power 18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta negative particles. Half-life it is 12.33 years. Table 9.1, here you can see the atomic and physical properties of hydrogen. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in the rates of reaction, mainly due to their different enthalpy of bond dissociation, table 9.1. However, in physical properties, these isotopes differ considerably due to their large mass differences. 9.3, preparation of dihydrogen, H2. There are a number of methods for preparing dihydrogen from metals and metal hydrides. 9.3.1, laboratory preparation of dihydrogen. Number 1. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. Zn plus 2H ion gives out Zn2 positive plus H2. Number 2, it can also be prepared by the reaction of zinc with aqueous alkali. Zn plus 2 NaOH gives out Na2 ZnO2 plus H2 sodium zincate. 9.3.2, commercial production of dihydrogen. The commonly used processes are outlined below. Number 1, electrolysis of acidified water using platinum electrodes gives hydrogen. 2H2 gives out 2H2 plus O2 on electrolysis in the presence of traces of acid or bases. Number 2, high purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. Number 3, it is obtained by as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reactions that take place at anode, 2 chloride ion gives out Cl2 plus 2 electron. At cathode, 2H2O plus 2 electron gives out H2 plus 2OH ion. The overall reaction is 2Na ion plus 2Cl negative plus 2H2O. Cl2 plus H2 plus 2Na plus 2OH ion, that is the product, and initial one was the reactant. Number 4, reaction of steam on hydrocarbons or coke at high temperatures in the presence of catalyst yields hydrogen. CnH2n plus 2 plus NH2O at 1270 Kelvin in the presence of nickel gives out NCO plus 2n plus 1 H2. Example, CH4 plus H2O gives out CO plus 3H2 and the presence was same as the above reaction. The mixture of CO and H2 is called water gas, as this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbon. It is also called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspaper, etc. The process of producing syngas from coal is called coal gasification. C plus H2O at 1270 Kelvin gives out CO plus H2. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate as catalyst. CO plus H2O gives out CO2 plus H2 in the presence of catalyst and at the temperature 673 Kelvin. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. Presently, approximately 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solutions, and 1% from other sources. 9.4 Properties of dihydrogen. 9.4.1 Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical properties along with those of deuterium are given in table 9.1. Already seen. 9.4.2 Chemical properties. The chemical behavior of dihydrogen and for that matter any molecule is determined to a large extent by bond dissociation enthalpy. The HH bond dissociation enthalpy is the highest for a single bond between two atoms of any element. What interference would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atoms is only approximate 0.081% around 2000 K, which increases to 95.5% at 5000 K. Also, it is relatively inert at room temperature due to the high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with one s1 electronic configuration, it does combine with almost all the elements. It accomplishes reaction by number 1 loss of the only electron to give H ion, number 2 gain of an electron to form H ion, and number 3 sharing electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reactions. Reaction with halogens. It reacts with halogen X2 to give hydrogen halides HX. H2 plus X2 gives out 2HX, and X is here fluorine, chlorine, bromine, iodine. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. 2H2 plus O2 and in the presence of catalyst, and it is forming 2H2O, and the delta H is minus 285.9 kilojoule per mole. Reaction with dinitrogen. With dinitrogen, it forms ammonia. 3H2 plus N2 at 673 Kelvin at 200 atmospheric pressure, and in the presence of Fe, it is forming 2NH3, and the delta H value is minus 92.6 kilojoule per mole. This is the method for manufacture of ammonia by the Haber process. Reaction with metals. With many metals, it combines at a high temperature to yield the corresponding hydrides. H2 plus 2M forming 2MH, where M is an alkali metal. Reactions with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metal, less active than iron, into corresponding metals. H2 plus Pd2 positive gives out Pd plus 2H ion. YH2 plus MXOY gives out XM plus YH2O. Reactions with organic compounds. It reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, number 1, hydrogenation of vegetable oils using nickel as catalyst gives edible fats, margarine and vanaspati ghee. Number 2, hydroformylation of olefins yields aldehydes which further undergo reduction to give alcohols. H2 plus CO plus RCH double bond CH2 and gives out RCH2CH2CHO. H2 plus RCH2CH2CHO gives out RCH2CH2CH2OH. 9.4.3 Uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizer. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soya bean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol, CO plus 2H2O, in presence of cobalt, catalyst, CH3OH it is forming. It is widely used for the manufacture of metal hydrides, and it is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. Atomic hydrogen atoms produced by dissociation of dihydrogen with the help of an electric arc are allowed to recombine on the surface to be welded to generate the temperature of 4,000 Kelvin. It is used as a rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases greater energy per unit mass of fuel in comparison to gasoline and other fuels. 9.5 Hydrides. Dihydrogen under certain reaction conditions combines with almost all elements except noble gases to form binary compounds called hydrides. If E is the symbol of an element, then hydride can be expressed as EHX, that is example MgH2, or EMHN, example B2H6. The hydrides are classified into 3 categories. Number 1, ionic or saline are salt-like hydrides. Number 2, covalent or molecular hydrides. And number 3, metallic or non-stoichiometric hydrides. 9.5.1 Ionic or saline hydrides. These are stoichiometric compounds of the dihydrogen formed with most of the S block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as LiH, BH2 and MgH2. In fact, BH2 and MgH2 are polymeric in structure. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of H negative ion. 2H negative, on melting it is forming H2 plus 2 electron, and that reaction happens at anode. Saline hydrides react violently with water producing dihydrogen gas. NaH plus H2O gives out NaOH plus H2. Lithium hydride is rather unreactive at moderate temperatures with O2 or Cl2. It is therefore used in the synthesis of other useful hydrides. Example 2,8-LiH plus Al2Cl6 gives out 2,Li-AlH4 plus 6,LiCl. 2-LiH plus B2H6 gives out 2-LiBH4. 9.5.2 Covalent or molecular hydride. Dihydrogen forms molecular compounds with most of the p block elements. Most familiar examples are CH4, NH3, H2O and HF. For convenience, hydrogen compounds of non-metals have also been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons and bonds in their Lewis structure into number 1 electron deficient, number 2 electron precise, and number 3 electron rich hydrides. An electron deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane, B2H6 is an example. In fact, all elements of group 13 will form electron deficient compounds. What do you expect from their behavior? They act as Lewis acids, that is electron acceptors. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All elements of group 14 form such compounds, example CH4, which are tetrahedral in geometry. Electron-rich hydrides have excess electrons which are present as lone pairs. Elements of group 15 to 17 form such compounds. NH3 has 1 lone pair, H2 2 lone pair and HF 3 lone pairs. What do you expect from the behavior of such compounds? They will behave as Lewis bases, that is electron donors. The presence of lone pairs on highly electronegative atoms like NOF in hydride results in hydrogen bond formation between the molecules. This leads to the association of molecules. 9.5.3 Metallic or non-stoichiometric or interstitial hydrides. These are formed by many D block and F block elements. However, the metals of group 7, 8, 9 do not form hydride. Even from group 6, only chromium forms CRH. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. For example, LaH 2.87, YbH 2.55, TiH 1.5 to 1.8, ZrH 1.3 to 1.75, VH 0.56, NiH 0.6 to 0.7, PDH 0.6 to 0.8, etc. In such hydrides, the law of constant composition does not hold good. Earlier, it was thought that in these hydrides, hydrogen occupies interstices in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel and PD, Ce and Ac, other hydrides of this class have lattice different from that of the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction hydrogenation reactions for the preparation of large number of compounds. Some of the metals, example PD and PT, can accommodate a very large volume of hydrogen and therefore can be used as its storage media. This property has high potential for hydrogen storage and source of energy. 9.6 Water. A major part of all living organism is made up of water. Human body has about 65% and some plants have as much as 95% water. It is a crucial compound for the survival of all life forms. It is a solvent of great importance. The distribution of water over the earth's surface is not uniform. The estimated world water supply is given in table 9.2. Table 9.2 estimated water supply you can see here in this table. Oceans 97.33, saline lakes and inland seas 0.008, polar ice and glaciers 2.04, groundwater 0.61, lakes 0.009, soil moisture 0.005, atmospheric water vapor 0.001% and rivers 0.0001%. 9.6.1 Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in table 9.3 along with the physical properties of heavy water. The unusual properties of water in the condensed phase, liquid and solid states are due to the presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point and high heat of vaporization and high heat of fusion in the comparison of H2S and H2SE. In comparison to other liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment, and dielectric constant, etc. These properties allow water to play a key role in the biosphere. Here you can see table 9.3 physical properties of H2O and D2O. Molecular mass, melting point, boiling point, enthalpy of formation, all the properties are mentioned here. You can see. The high heat of vaporization and heat of capacity are responsible for moderation of the climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrate dissolve in water. 9.6.2 Structure of water. In the gas phase, water is a bent molecule with a bond angle of 104.5 degree and OH bond length of 95.7 pm as shown in figure 9.1. See this figure. It is a highly polar molecule. Its orbital overlap picture is shown in figure 9.1c, and in the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperatures, it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation, which ensures the survival of the aquatic life. This fact is of great ecological significance. 9.6.3 Structure of ice, but before that see the 9.1a, b and c, all the figures. Now, structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure as shown in figure 9.2. See here. Examination of ice crystals with X-ray shows that each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 pm. Hydrogen bonding gives ice a rather open to type structure with wide holes. These holes can hold some other molecules of appropriate size interstitially. 9.6.4 Chemical properties of water. Water reacts with a large number of substances. Some of the important reactions are given below. Number 1, amphoteric nature. It has the ability to act as an acid as well as a base. That is, it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with NH3 and a base with H2S. H2O plus NH3 gives out OH negative plus NH4 ion. H2O plus H2S gives out H3O positive plus HS ion. The autoprotolysis self-ionization of water takes place as follows. H2O plus H2O, reversible reaction H3O positive plus OH ion. Number 2, redox reactions involving water. Water can be easily reduced to dihydrogen by highly electropositive metals. 2H2O plus 2Na gives out 2NaOH plus H2. Thus, it is a great source of dihydrogen. Water is oxidized to O2 during photosynthesis. 6CO2 plus 12H2O gives out C6H12O6 plus 6H2O plus 6O2. With fluorine also, it is oxidized to O2. 2F2 plus 2H2O gives out 4H ion plus 4F negative plus O2. Number 3, hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. P4O10 plus 6H2O gives out 4H3PO4. SiCl4 plus 2H2O gives out SiO2 plus 4HCl. N3 negative plus 3H2O gives out NH3 plus 3OH ion. 4. Hydrates formation. From aqueous solution, many salts can be crystallized as hydrated salts. Such an association of water is of different types. Number 1, coordinated water. Example, CrH2O whole 6 and the whole 3 positive and 3Cl negative. Number 2, interstitial water, example BaCl2 into 2H2O. Number 3, hydrogen bonded water, example CuH2O whole 4 the whole 2 positive, SO4 2 negative into H2O and CuSO4 into 5H2O. 9.6.5 Hard and soft water. Rainwater is almost pure, may contain some dissolved gases from the atmosphere. Being a good solvent, when it flows on the surface of the earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard, and hard water does not give leather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives leather with soap easily. Hard water forms come and precipitate with soap containing sodium stearate, C17H35COONA, reacts with hard water to precipitate out calcium or magnesium stearate. 2C17H35COONA plus M2 positive gives out C17H35COO the whole twice M and plus 2Na positive, where M is calcium or magnesium. It is therefore unsuitable for laundry. It is harmful for boiler as well because of deposition of salts in the form of scale. This reduces the efficiency of the boiler. The hardness of the water is of two types, temporary hardness and permanent hardness. 9.6.6 Temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonates. It can be removed by number 1, boiling. During boiling, the soluble MgHCO3 whole twice is converted into insoluble MgOH whole twice and CaHCO3 whole twice is changed to insoluble CaCO3. It is because of high solubility product of MgOH whole twice as compared to that of MgCO3 that MgOH whole twice is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. MgHCO3 whole twice on heating forming MgOH whole twice plus 2CO2 and CHCO3 whole twice on heating it is forming CaCO3 plus H2O plus CO2. Number 2, Clark's method. In this method, calculated amount of lime is added to hard water and it precipitates out calcium carbonate and magnesium hydroxide which can be filtered off. CaHCO3 whole twice plus CaOH whole twice gives out 2CaCO3 plus 2H2O. MgHCO3 whole twice plus 2CaOH whole twice gives out 2CaCO3 plus MgOH whole twice plus 2H2O. 9.67 Permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following methods. Number 1. Treatment with washing soda, sodium carbonate. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonate. MCl2 plus Na2CO3 gives out MCO3 plus 2NaCl. MSO4 plus Na2CO3 gives out MCO3 plus Na2SO4. Number 2, Kalgan's method. Sodium hexametaphosphate Na6P6O18, commercially called Kalgan. When added to hard water, the following reactions takes place. Na6P6O18 gives out 2Na positive, Na4P6O18 2 negative, where M is equals to magnesium and calcium. M2 positive plus Na4P6O18 2 negative gives out Na2MP6O18 2 negative plus 2Na ion. The complex anion keeps the magnesium 2 positive and calcium 2 positive ions in solution. Number 3, ion exchange method. This method is also called zeolite or permuted process. Hydrated sodium aluminum silicate is zeolite or permuted. For the sake of simplicity, sodium aluminum silicate NaLSI4 can be written as NaZ. When this added to hard water, exchange reaction takes place. 2NaZ plus M2 positive gives out MZ2 plus 2Na positive, where M is magnesium or calcium. Permuted zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with an aqueous sodium chloride solution. MZ2 plus 2NaCl gives out 2NaZ plus MCl2. Number 4, synthetic resins method. Nowadays, hard water is softened by using synthetic cation exchanges. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin RSO3H is changed to RNA by treating it with NaCl. The resin exchanges sodium ions with calcium 2 positive and Mg2 positive ions present in hard water to make the water soft. Here R is resin anion. 2RNA plus M2 positive gives out R2M plus 2Na positive. The resin can be regenerated by adding aqueous NaCl solution. Pure demineralized or deionized water-free form all soluble mineral salts is obtained by passing water successively through a cation exchange in the form of H-ion form and an anion exchange in the form OH negative form. Reasons: 2RH plus M2 positive, reversible reaction Mr2 plus 2H ion. In this cation exchange process, H ion exchanges for sodium ion, calcium ion and magnesium ion and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, RNH2 plus H2O gives out RNH3 positive into OH and RNH3 positive into OH negative plus X negative gives out RNH3 positive X negative plus OH negative. OH negative exchanges for anions like Cl ion, HCO3 ion and SO42 negative etc. present in water. OH negative ions thus liberated neutralize the H ions set free in the cation exchange. H ion plus OH negative gives out H2O. The exhausted cation and anion exchange resin beds for regenerated by treatment with dilute acid and alkali solutions respectively. 9.7 Hydrogen peroxide H2O2. Hydrogen peroxide is an important chemical used in pollution control treatment by domestic and industrial effluents. 9.7.1 Preparation. It can be prepared by the following methods. Number 1. Acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. BaO2 into 8H2O plus H2SO4 gives out BaSO4 plus H2O2 plus 8H2O. Number 2. Peroxodisulfate obtained by electrolytic oxidation of acidified sulfate solutions at high current density. On hydrolysis yields hydrogen peroxide. 2HSO4 negative on electrolysis gives out HO3SOO SO3H. On hydrolysis, it gives 2HSO4 negative plus 2H ion plus H2O2. This method is now used for the laboratory preparation of D2O2. K2S2O8 plus D2D2O gives out 2KDSO4 plus D2O2. Number 3. Industrially, it is prepared by the auto-oxidation of 2-alkyl anthraquinols. 2-ethyl anthraquinol, it is giving H2O2 plus oxidized product and the presence is O2 and H2 and PD. In this case, 1% H2O2 is formed. It is extracted with water and concentrated to approximately 30% by mass by distillation under reduced pressure. It can be further concentrated to 85% by careful distillation under low pressure. The remaining water can be frozen out to obtain pure H2O2. 9.7.2 Physical properties. In the pure state, H2O2 is an almost colorless, very pale blue liquid. It is important physical properties are given in table 9.4. H2O2 is miscible with water in all proportions and forms a hydrate H2O2 into H2O. A 30% solution of H2O2 is marketed as 100 volume hydrogen peroxide. It means that 1 milliliter of 30% H2O2 solution will give 100 ml of oxygen at STP. Commercially marketed sample is 10B, which means that the sample contains 3% H2O2. Table 9.4 Physical properties of hydrogen peroxide. You can see melting point 272.4, boiling point 423, vapor pressure 1.9, density 1.64, density and liquid at 298 Kelvin, that is 1.44, viscosity, that is 1.25, dielectric constant 70.7 and electrical conductivity is 5.1 into 10 to the power minus 8. 9.7.3 Structure. Hydrogen peroxide has a non-planar structure. The molecular dimensions in the gas phase and solid phase are shown in figure 9.3. See this diagram. 9.7.4 Chemical properties. It acts as an oxidizing as well as reducing agent in both acidic and alkaline media. Simple reactions are described below. Number 1. Oxidizing action in acidic medium. 2Fe2 positive plus 2H ion plus H2O2 gives out 2Fe3 positive plus 2H2O. PbS plus 4H2O2 gives out PbSO4 plus 4H2O. Number 2. Reducing action in acidic medium. 2MnO4 negative plus 6H ion plus 5H2O2 gives out 2Mn2 positive plus 8H2O plus 5O2. HOCl plus H2O2 gives out H3O positive plus Cl negative plus O2. Number 3. Oxidizing action in basic medium. 2Fe2 positive plus H2O2 gives out 2Fe3 positive plus 2OH negative. Mn2 positive plus 2H2O2 gives out Mn4 positive plus 2OH negative. Number 4, reducing action in basic medium. I2 plus H2O2 gives plus 2OH negative gives out 2I negative plus 2H2O plus O2. 2MnO4 negative plus 3H2O2 gives out 2MnO2 plus 3O2 plus 2H2O plus 2OH ion. 9.7.5 Storage. H2O2 decomposes slowly on exposure to light. 2H2O2 gives out 2H2O plus O2. In the presence of metal surfaces or traces of alkali, the above reaction is catalyzed. It is therefore stored in wax-lined glass or plastic vessel in dark. Urea can be added as a stabilizer. It is kept away from dust because dust can induce explosive decomposition of the compound. 9.7.6 Uses. Its wide-scale use has led to tremendous increase in the industrial production of H2O2. Some of the uses are listed below. 1. In daily life, it is used as a hair bleach and as a mild disinfectant. As an antiseptic, it is sold in the market as a perhydrol. Number 2, it is used to manufacture chemicals like sodium perborate and percarbonate, which are used in high-quality detergents. Number 3, it is used in the synthesis of hydroquinone, tartaric acid, and certain food products and pharmaceuticals, cephalosporin, etc. Number 4, it is employed in the industries as bleaching agent for textiles, paper pulp, leather, soils, fats, etc. Number 5, nowadays it is also used in environmental green chemistry, for example, in pollution control treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic condition to sewage waste, etc. 9.8 Heavy water D2O. It is extensively used as a moderator in nuclear reactor and in exchange reaction for the study of reaction mechanism. It can be prepared by exhaustive electrolysis of water or as byproduct in some fertilizer industries. Its physical properties are given in table 9.3. It is used for preparation of other deuterium compounds. For example, CaC2 plus 2D2O gives out C2D2 plus CaOD whole twice. SO3 plus D2O gives out D2SO4. Al4C3 plus 12D2O gives out 3CD4 plus 4AlOD whole thrice. 9.9 Dihydrogen as fuel. Dihydrogen releases large quantities of heat on combustion. The data on energy released by combustion of fuels like dihydrogen, methane, LPG, etc. are compared in terms of the same amounts in mole, mass and volume are shown in table 9.5. From this table, it is clear that on a mass for mass basis, dihydrogen can release more energy than petrol, about 3 times. Moreover, pollutants in combustion of dihydrogen will be less than petrol. The only pollutants will be the oxides of dinitrogen due to the presence of dinitrogen as impurity with dihydrogen. This, of course, can be minimized by injecting a small amount of water into cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. However, the mass of the containers in which dihydrogen will be kept must be taken into consideration. A cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. Also, dihydrogen gas is converted into liquid state by cooling to 20 K. This would require expensive insulated tanks. Tanks of metal alloy like Na-Na5, TiTiS2, MgMgS2, etc. are in use of storage of dihydrogen in small quantities. These limitations have prompted researchers to search for alternative techniques to use dihydrogen in an efficient way. In this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gas is dihydrogen. Advantage of hydrogen economy is the energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as fuel was launched in October 2005 for running automobiles. Initially, 5% dihydrogen has been mixed in CNG for use in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for generation of electric power. It is expected that economically viable and safe sources of dihydrogen will be identified in the years to come for its usage as a common source of energy. Table 9.5, the energy released by combustion of various fuels in moles, mass and volume. You can see this table. Summary. Hydrogen is the lightest atom with only one electron. Loss of this electron results in an elementary particle, the proton. Thus, it is unique in character. It has 3 isotopes, namely protium, deuterium, and tritium. Among these 3, only tritium is radioactive. In spite of its resemblance both with alkali metals and halogens, it occupies a separate position in the periodic table because of its unique properties. Hydrogen is the most abundant element in the universe. In the free state, it is almost not found in the Earth's atmosphere. However, in the combined state, it is the third most abundant element on the Earth's surface. Dihydrogen on the industrial scale is prepared by the water-gas shift reaction from petrochemicals. It is obtained as a byproduct by the electrolysis of brine. The H bond dissociation enthalpy of dihydrogen 435.88 kJ per mole is the highest for a single bond between two atoms of any elements. This property is made use of in the atomic dihydrogen torch, which generates a temperature of approximately 4000 K and is ideal for welding of high melting metals. Though dihydrogen is rather inactive at room temperature because of very high negative dissociation enthalpy, it combines with almost all the elements under appropriate condition to form hydrides. All the types of hydrides can be classified into the three categories: ionic or saline hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Alkali metals hydrides are good reagents for preparing other hydride compounds. Molecular hydrides, example B2H6CH4, NH3H2O, are of great importance in day-to-day life. Metallic hydrides are useful for ultra purification of dihydrogen and as dihydrogen storage media. Among the other chemical reactions of dihydrogen reducing reactions leading to the formation of hydrogen halides, water, ammonia, methanol, vanaspati ghee, etc. are of great importance. In metallurgical processes, it is used to reduce metal oxides. In a space program, it is used as a rocket fuel. In fact, it has a promising potential for use as non-polluting fuel as of the near future, hydrogen economy. Water is the most common and abundantly available substance. It is of a great chemical and biological significance. The ease with which water is transformed from liquid to solid and to gaseous state allows it to play a vital role in biosphere. The water molecule is highly polar in nature due to its bent structure. This property leads to hydrogen bonding, which is a maximum in ice and least in water vapor. The polar nature of water makes it a very good solvent for ionic and partially ionic compounds, B, to act as an amphoteric acid as well as base substance, and C, to form hydrates of different types. Its property to dissolve many salts, particularly in large quantity, makes it hard and hazardous for industrial use. Both temporary and permanent hardness can be removed by the use of zeolites and synthetic ion exchangers. Heavy water, D2O, is another important compound which is manufactured by the electrolytic enrichment of normal water. It is essentially used as a moderator in nuclear reactors. Hydrogen peroxide, H2O2, has an interesting non-polar structure and is widely used as an industrial bleach and in pharmaceutical and pollution control treatment of industrial and domestic effluents. चैप्टर डन बच्चों. सो अगर आपकी ये वीडियो हेल्प कर रहा हो तो इसको लाइक करिएगा, और अगर आप मेरे चैनल को अभी तक सब्सक्राइब नहीं किया है तो प्लीज अब सब्सक्राइब कर लीजिए, क्योंकि मैं डेली आप लोगों के लिए ऑडियो बुक्स अपलोड कर रही हूँ. सो आई होप कि आपके एग्जाम में जरूर हेल्प कर रही होंगी, और इनको शेयर करिए अपने दोस्तों के साथ में ज्यादा से ज्यादा, ताकि उनकी भी मदद कर सके, उनको भी पता चल सके कि हाँ, इस तरह की ऑडियो बुक्स भी अवेलेबल हैं. So see you soon in my next video. Till then, just stay tuned with me. Bye bye. Take care.